Hey physics, this is Mr. Hausman coming to you from his iPad, making a little lesson about vectors and scalars so we can get a really good jump start on next week's key objectives. We want to study motion in 2 dimensions, that is to say projectiles, but before we do that, we're going to have to spend just a little bit of time on this idea, vectors and scalars. And you're thinking to yourself, already did that, I can already classify them. You're right, the first objective is probably something you already know, but what we haven't seen is how to draw them and how to add them. There's some systems that you'll learn in physics, and then there's some systems you may learn in a math class that add vectors using an algebraic approach. We're going to be using a graphical approach, but let's not get ahead of ourselves. Let's begin here. Okay, so measurements in science. Everything in the world that can be measured, every quantity, like mass, like length, like time, like velocity, everything can be divided into really 2 separate categories. We have either scalar quantities, and I'll have to admit, I spell that wrong sometimes, but it's definitely a S-C-A-L-A-R, and then the other kind of quantity is a vector. And that's not new to us because we've already been talking about vectors and differentiating speed from velocity and the like. But scalars, right, examples might be something like mass, right, of a parachute. And how would we describe that? Well, the mass is measured in kilograms. And that's all you need to do. Maybe that parachute is 3.2 kilograms. We were building parachutes recently in class. And that fully describes the mass of the parachute. You could also say the length of a parachute string would be about maybe 20 centimeters long. Time is another. And then, of course, there's all the ones like distance, speed, and quite honestly, many more. We had a little contest, who could come up with more a few weeks back. And what they all have in common is that all they have is a magnitude and then the unit that applies to that particular scalar quantity. But we'll be talking about that in just a minute. Vectors, of course, might include a velocity, such as how fast your parachute was, terminal velocity was going. And we measured in one of my other classes that some of our parachutes are dropping at about 5 meters per second, miles per hour. We happen to have a radar gun calibrated in miles per hour, and that would be downward, okay? So that would be negative 5 miles per hour. It could also be a displacement, and various displacements could be Mr. Hausman traveled 75 meters north, nope, let's say south, to the maroon office. That's about how far it is, down D200. And by saying south or toward the maroon office, that's a direction. So vectors come in many kinds. Others that we haven't encountered yet are forces. Others include torque. And there's quite a few that we will encounter this year. So scalars versus vectors. Everything can be divided as one or the other. But, I'm getting ahead of myself, what do they all have in common? And there's room on your sheet just below, so why don't we carve out a little space here? And that's really all we need, is vectors are quantities that have a direction to them and an amount or magnitude. That's the 2 key parts they always have to have. So over here, we had the downward direction, also represented by the negative sign, and then we also said south on the displacement vector. So you have to add in that direction component. Well, the other thing is that vectors are represented as arrows. And obviously, or perhaps not obviously, right, when you draw a vector, the arrowhead shows the direction, right? That's what the arrowhead means. That's kind of a convention. We've known that for most of our lives. However, the tail, the entire body of the arrow, represents the magnitude. And that's going to lead us to a discussion of really how to draw these accurately, how to draw them to scale. Okay, so vectors. Now, what does that mean? Well, scalars are quantities that have magnitude only. How do you add those? Well, you just do a regular arithmetic. You just do simple addition. How do you add two masses? You put them in the same unit system. They have to both be kilograms, and then you can add kilograms to kilograms, and it's no harder than that, okay? Let's talk about vector addition. What do they have? Okay, so it's on the bottom of page 2 of your notes, but there's really two systems, and we are definitely going to be focusing on the head to tail method primarily for this lesson, but there is a secondary system. It's not secondary like worst choice. It gets used at a different time of the year. We're going to use this, I'll be honest, we're going to use this with forces, and we're going to need to use it with forces, whereas with projectiles, we're going to want to use head to tail. Okay, but again, that's a foreshadowing. Vector addition. Well, vector addition is kind of complicated because of the directions. So the easiest way to do this is to draw your vectors. That color probably doesn't stand out much. Let's do black. I think we're having a little trouble with color here. Let's try that again. Right, draw your vectors, connecting them sequentially. And you can put them in any order you want, but you have to connect them like 1 to 2 to 3 to 4 sequentially. But here's the catch. You must do so connecting the head of the first one to the tail of the next one, second. And that goes on and on. Head of the second to the tail of the third, and so forth and so on. Okay, so let's do an example of that. Let's simply do a vector of displacement. And let's start over here. Hi. Just had a visitor. Sorry if you heard that. We were just talking about our parachute project. Anyway, so now we've drawn these two vectors. Now, we haven't added them. All we did was draw them to scale, and we set them up to be added. Now, I think there's no one in this, listening to this podcast who can't figure out that 3 east plus 1.5 east is equal to 4.5 total meters of displacement east. And you're like, so then why do I need to do the head to tail method? Can't I just look at those two numbers? Well, the reason why is because this is applicable to any vectors, any number of vectors, any direction vectors. So what you do to actually find your resultant, that's a key word. A resultant is the sum of vectors. And how you draw that is you start at the tail of the first, and you go straight, no matter what direction it is, to the head of the last vector. And sometimes that gets a little complicated. We'll do some examples of this, but it's a straight line from the head, from the tail to the head of the last vector. And it has a direction to it, right? And so we'll do an example of that. So where's the tail of the first one? And we can clearly see that the tail of the first vector that I drew was 3. It's back here. So I'm going to start my red pen, and I'm going to use a different color. I'm going to use contrast. And then, of course, I can see that the head of the last vector is way out here. So I'm going to draw a new vector straight from, the tail to the head. Now, I can't draw it on top of, because then you can't even see it. You would no longer be able to see the 3 and the 1.5. But if you do this to scale, and you are strict about that scale, and you add up the total length of this line, and then you multiply by the scale factor, you should get exactly 4.5. So we're going to label that as 4.5 meters east. Okay? So, and you say, well, you didn't touch the tail, but you line them up, and you line it up with the head. And in the case of straight line vectors, you kind of have to shift it off. You have to shift it a little distance away, but you put it as close as you can. And certainly you put them parallel. So graphical vector addition is nothing more than drawing vectors connecting them head to tail. By the way, some people call it tip to tail. The tip of an arrow is the back end. Tip to tail. I don't know why that got misspoken there. Okay, I just prefer head to tail because there's your head, there's your tail of your next, and then that would keep going. Okay, now I did allude to the fact that there's another method for drawing vectors, and that is called the parallelogram method. And it doesn't make sense with the example we did above. But how about let's talk about forces. In fact, you might have seen a picture in class where I talked about free fall and terminal velocity, and we had a skydiver, falling through the air, and the air resistance underneath all the air molecules trying to get out of the way and creating a force. And you may have noticed that I drew a force, and I'm going to use black again, that the weight of this skydiver, the pull of Earth down on him, and I guess I could draw right on the stick figure, but what we're going to do is we're going to learn that this is called the free body. It's a dot or a box that stands for the real object, and you put all of the forces, which are vectors, on that object and whichever way they are affecting the object. But what you'll notice, right, and then air resistance or drag goes against it, goes up. And you'll notice that I definitely did not connect those head to tail. In fact, I put them tail to tail. So that's actually the beginning of how a parallelogram is made, and you're like, that's still not a parallelogram. But we will learn another way involving parallelograms or tail-to-tail method, but it can get really confusing when you're dealing with velocities and when you're dealing with non-forces, vectors. So we'll leave it at that. It's a preview. Here, let me give you a small, quick example. If sometimes your forces are not opposite each other, they're at 90 degrees, you still put your forces connected tail to tail. Let's call that force 1, and this is force 2. And then you say, well, I don't see the resultant because I can't go from the tail of the first vector. They're connected together, and there certainly isn't a head of the last vector. But what you do is you make a parallelogram out of your two component vectors, and you go to the opposite corner. That's a parallelogram. Okay, now I forgot a vocab word. The key word here that we forgot is component vectors. Components are the things that get added. A resultant is the answer. So the two components add up to the resultant. Let's move on to the next slide and do some more examples. Okay, get a ruler. Now it's time to be precise. Now, my iPad doesn't really allow me to measure in inches. That's one drawback to at least this program. So I think we're on page 3 of our notes, and we've got a moving sidewalk. And it has a belt that is moving forward or to the right. It has its own velocity before you even stand on it. Now, that's a little bit more than an inch on that screen. It may be different on the screen you're looking at, but we're going to say this represents 1 meter per second. That's the velocity of the moving belt without anyone on it. But you've been on a moving sidewalk maybe at some point in your life, and you can walk at sometimes faster than the belt. It's just maybe it's a really long distance. You get tired. So we're going to say your speed is 2 meters per second. So if someone said, 1, determine the resultant velocity of you walking forward on the sidewalk, what you would do is you would draw your 1 meter per second velocity, and you might be tempted to draw your speed on top of it because we know that you stand on top of it and they kind of superimpose. But what you do with vector addition is you connect them head to tail. So here's the belt's velocity, and here's the person. And remember we said it was twice as fast. So I'm going to make a line that instead of 1 inch should be 2 inches long, or about twice as long. And I'm going to label that 2 meters per second, and I could call that V of the person. And I could have called this V of the belt. And we connected them because they're both going forward. Because when you walk with the sidewalk, you go the same way as it, right? And then to show the resultant, you would go back to the tail of the first one, go all the way to the head of the last one, try to make those line up as best you can. And again, if you measure this, this should be 3 inches, and that corresponds back to a 3 meter per second resultant velocity. So the person's velocity isn't really 2. When you stand on a moving sidewalk, according to the surroundings, people would see you having a speed of 3, okay? What if you walk against it? I have to say I was delayed at an airport once. I was with a bunch of students, and we, there might have been a challenge to see who can walk backwards and like maintain their position. I bet you can see what I'm doing with this. So what if you walk the same speed? But that's not what this problem is. What if the belt is still going forward? Draw it 1 inch, please, and it's 1 meter per second. Now, I hope I left enough room. Nope, I didn't. So we're going to do a quick cleanup here. I'm going to shift it over here. Can you see why? Here's 1 meter per second. That's the V of the belt. And then I'm going to connect the person's velocity. And you're probably saying, how do you connect head to tail if it's like opposite? Do you just like kind of superimpose it? No, you kind of use the same thing we did already with the resultant. You go to the tip of that arrow, and since that's a certain like position, now you show the person's velocity going against the sidewalk. There's 1. There's 2 inches, and that's now a -2 meter per second velocity. And I'm sorry that those don't look perfectly parallel. And now it maybe gets a little confusing. Maybe you thought it was easier to just solve, you're going backwards, -1, but let's see how this will work. So according to the system, you go to the tail of the first one, and you go to the head of the last one. But in this case, you don't cut a diagonal. You don't kind of go this way, because remember, the separation between these two doesn't really stand for anything. It's just the fact that you can't have vectors right on top of each other. So what you do is you just simply go from the tail to the head of the last one. And sorry, not straight. This is where a ruler matters. And what you'll notice is that if someone said, what is the magnitude and direction of the resultant? You would clearly be able to show that its direction is west, or right, the negative direction, and the magnitude of that vector, according to the scaled diagram, this should be 1 inch, and so since 1 inch equals 1 meter per second, okay? And it adds up, of course. 1 plus -2 is -1 meter per second. So now the person's real speed would be going backwards at -1 meter per second, okay? Okay, here's the challenge. 3. What if you're crossing this sidewalk? Now you say to yourself, that's impossible. They're too narrow. But what you can do is sometimes take a side step to let someone go by. So this is now a top view of the belt. And say you're standing here. This is the top of your head. And you know that the belt is moving at 1 meter per second. And you decide to sidestep. And let's just not debate this. You can walk sideways just as fast as you can walk forward or backwards, probably. And so what you realize is that if you're trying to head toward this side, let's do that with the laser beam. You're trying to walk to this side of the sidewalk, maybe to allow someone to pass you. You are going to have to connect your vectors head to tail. Okay. Now you're like, but you just went past the railing. If this is a top view, these are the handrails on the side. The belt is below your feet. And I don't want to draw over the vectors. It'll get confusing. So top view means that now your velocity does not have to correspond with the picture. But, right, here's the belt's velocity. Here's your velocity. It should be 2 inches long, and it's going across. Now, we don't know if it was across the other way, like to the person's left or to the right. But let's just assume it's 2 meters per second across the belt. So here's how you would find your actual speed. You would go from the tail of the last one. And now we no longer have to deal with that whole parallel thing. That parallel thing is actually a tough place to start because it makes you think you have to shift everything. Well, what you really want to do with vectors is you go literally from the tail of the first with your ruler straight to the tip of the arrow of your last vector. Look back a slide, look at your notes, and you go from the tail of the first to the tip of the last one. And it should be straight. Again, don't have a straight edge on this app. And here is my resultant. And there is no special triangle for a 90-degree angle, 1, 2. There are some special triangles like 3, 4, 5s. Oh, wait a minute. Is it 1, 2, rad 3? Actually, I stand corrected. There is a special triangle here. But you can memorize all the special triangles you want, but essentially what you're going to really need to be able to do, and it's not that hard, is to solve that resultant using some basic trig. And what we probably recognize is that r squared is equal to the velocity of the person which is in the horizontal direction, squared, because that's side one of a right triangle. And then the other leg of the triangle is the velocity of the belt. Doesn't matter what order you do it in, squared will actually equal the resultant squared, which is going to be the actual speed. So this should be pretty easy. 1 meter per second squared plus 2 meters per second squared is going to be equal to 5 meters squared per second squared. Check my math, 2 squared, 1 squared, add it together, 5. And so my resultant is going to be the square root of 5. And that is obviously doable on a calculator. I know it is irrational. I'm going to take out my calculator on my phone. 5, we could estimate it, but let's just get an exact number, 2.2. 2.24 meters per second. I guess I made extra sig figs. Really, the answer could be 2, which gets a little confusing because you know that hypotenusae should be longer than either side. So 2.2, not corresponding properly to sig figs, but it's still the V of the actual walker. So when you cut across that belt, you're not going 1, you're not going 2, your actual speed would be 2.24 meters per second. That's the sum of your two vectors on a diagonal. Now, we're going to have to talk some geometry because we need to brush up on how to find that angle. And if you're perfectly solid with that, awesome. We're going to do it shortly right here. Tan -1 of the ratio 2/1 should equal theta. And if that just made a lot of jumps to you and you haven't done that in a while, we will definitely review it. Okay, so that's page 3. Let's add some on page 4. 5 east and 8 west. So draw 5 inches east. And this is now centimeters. It says centimeters. You could use, let's use a scale here of 1 centimeter equals 1 centimeter. Makes sense, kind of, right? So 5 centimeters east and then 8 centimeters west. And notice I'm going right below the arrow. And I'm going past it, 8 centimeters. And then my resultant, I think blue had been my resultant color before, goes from the tail of my first to the tip of my last vector. Oops, I'm writing over my 1. And really this becomes +5 plus -8, or a total of -3 centimeters. Measure that line, and it should be 3 centimeters if you did it to scale. Okay? 4 and 6, but we're going to mix them up, and we're going to do them 90 degrees to each other. So watch this. It says 4 centimeters south first, but it doesn't matter which one you draw first. I'm going to go 6 centimeters east to begin with. Now I'm going to also make sure that I have room to go south on my picture. So 6 centimeters east, followed by 4 centimeters south. Head to tail is how I drew them. It'll become a habit. And on graph paper, it's a little bit easier, right? Straight lines as best as you can. You're using a ruler and you got graph paper. So then your resultant goes from the tail of the first one to the head of the last one. It's really the same as the previous picture, except for you don't have to do an offset. So with a ruler, completely straight all the way down there. And don't forget your arrowhead. All 3 of these are vectors. They resemble a triangle, but it's a vector diagram. So here's my resultant. And you know that you would find this by doing resultant equals, I'm going to make a jump here, see if you can do this, right? Your displacement 1 squared plus a displacement 2 squared, right? Those are my 6 and my 4. And I'm going to show that when you take 6 centimeters squared plus 4 centimeters squared, and then you square root everything, because that's how you undo the Pythagorean theorem, we get 36 plus 16. Is that going to be 52? 6 and 6 is 12. Carry the 1. Yep, higher math. And the square root of 52 is going to be, let's see. Sorry, jumping over to my calculator. 52. And I get, there we go, let's keep the square root in there. I get 7.2 centimeters. Okay, now that's the magnitude of the resulting vector. A quick review, one more time, but I also need to know its direction. How far away from east did I have to turn to go straight toward the 4 centimeters?